Hello, this is Information Service Engineering, lecture number 4, Linked Data Engineering. In this part of the lecture, we are going to talk about the web ontology language, OOL. And let us start. So do you remember the ontologies? We spoke about ontologies before. So here we have a simple ontology. And what do we have here? So we have a person here in the center of our small ontology, a class person, and 4 subclasses of person: woman, man, astronaut, and student. What else we have? We have a link, so this person is linked to an address through the property has address. So far so good. This is what we can also describe with what we have learned up to now, which is RDF and RDFS. But what if we want to enrich this ontology by including some constraints to it? For example, we want to make sure that woman and man, those 2 classes, are disjoint, meaning that if there is a woman, if there is an instance of type woman, it cannot be a man in the same time. Or another constraint, some cardinality constraints, as they are known from the relational databases. For example, here, the relation between a student and a person, we wanted to make it like one-to-one relation. Or the has address relation between a person and an address, we want to make sure that it's an N-to-M relation, meaning that a person can have multiple addresses and a certain address can be the address of many different persons. What do we do for that? Well, for sure, RDF and RDFS cannot help us here, since they lack semantic expressivity to represent fully fledged ontologies. So what do? How can we enrich our ontologies? And the solution is called OOL. Here is the web ontology language OOL. It's a language of knowledge representation for authoring ontologies. It's a semantic fragment of first-order logic and comes to different flavors. Here we see some of the flavors. So we have the OOL-EL, OOL-RL, and OOL-QL, which are less complex than the one comes after, which is the OOL-DL. So in these lectures, we are going to focus on OOL-DL. This is more expressive, it has more expressivity, and also there are computational guarantees here in OOL-DL. Because after that, it comes the OOL-to-full, which is again very expressive, but it's not computable anymore. That's why we focus in the OOL-DL in these lectures. So, OOL is based on description logics. And here are some of the features and characteristics in description logics that also can be represented in OOL-DL. Of course, if we could have picked another version of the OOL-EL, RL, or QL, for example, we wouldn't be able to represent all those features. I'm not going to go one by one through this list because you will see during this part of the lecture about OOL, we are going to see some of those characteristics, how they work in practice with OOL. And let us actually start with OOL. So this is the namespace we use for OOL, the one that you see here on top. For OOL, there is again a turtle syntax, as the one we saw for RDF as well, so it will look familiar to us. And there are 3 main building blocks. The first of them is the classes, which is comparable with whatever we know as a class in RDFS up to now. That's simple. Then they come the individuals, again comparable with the class instances that we know from RDFS. And last we have again the properties, comparable to what we know as being a property in RDFS. So let's go through this list of the building blocks one after the other and see more details. So starting with the classes. They exist 2 predefined classes in OOL. The first one is called OOL-Thing and is the class that contains everything, all the individuals. All the individuals in an OOL ontology are of type thing. And the second one is the OOL-Nothing, which is the empty class. So what I want to mention here is that you see this gray box in the right corner of the slide, and this is the equivalent expressions in description logics. So from now on, you will see every time we have an OOL expression, we will have the equivalent expression in description logics for those that they are familiar to description logics, and they will help them understand better, but I'm not going to emphasize on this for the moment. So let's continue the classes and see how we define a class in OWL. Here we have a simple example which says book A OWL class. This is an RDF turtle serialization, so an OWL in RDF turtle serialization actually, so it's familiar to us. What is new here is this A. So A here is the equivalent to RDF type. So whenever you see A from now on, we mean RDF type. So this means like book is RDF type OWL class. This is the type of the book. And let's continue with the individuals. So as we know from the RDF, again here the individuals are defined as being members of a class. And we have here a simple example which says that 1984 is a type of a book, as we define it up to now in RDF. The difference here in OWL is that we can also define individuals that are not members of a certain class. And this we do it via the property OWL named individual. So you see here we have a small example and we say Harald Zak is of type named individual. That means this is an individual, we define it as being one, but we do not directly associate to a certain class. So this is a difference that we have here between RDF and OWL. And let's continue to the properties. So there exist two kinds of properties here in OWL, the object properties and the data type properties. Starting with the object properties are those that they have classes as a range. So the difference between those two types of properties, object and data type, it's in the range. So the object properties, they have classes as a range. And here is how we define an object property. We say that author is of a type OWL object property. Simple as that. And then if we want, we have to restrict the domain and the range of this property, and we do it in the following way. So of course comes a definition, and then we say that author, RDFS domain book, so we use the known to us properties, RDFS domain and range, and then also we specify the range and say that author, RDFS range, writer. And let's see now the data type properties. So the data type properties are the ones that they have data types as range. Again, we define them in this simple way. We say that publication year is a type OWL data type property, simple as that. And again, we want to specify the domain and the range of this property. So what do? Same properties here. We define that publication year is a data type property, and it has RDFS domain book, so same as previously, and the RDFS range here is XSD integer. So it's not a class, it's a data type. So let's see a full example that contains properties, definitions, and individuals together. So let's start. What do we do in the beginning? We define a class. So book is a class, writer is a class as well. Then we have author as being an object property. That's why we have author A, OWL object property. We define the domain being book and the range being writer. Then it comes another property, the publication year, which is a type of OWL data type property. So this is a data type property. We define again the domain here being a book and the range an XSD integer, as it's a data type property. And let's see how we use now these classes and properties by defining instances. So we start and we define an instance George Orwell as typewriter, and then 1984 as being a book. And then there is a property between 1984 and George Orwell, which is author. So 1984 has as author George Orwell, which is correct, does not violate our definitions, since author is an object property with a range writer, and George Orwell is a writer. And then 1984 has as publication year 1984, which is an integer, so again does not violate our definitions of the data type property, publication year. So let us continue. In OWL, we have again hierarchies. We can define hierarchies among classes, as we saw in RDFS. And to do that, we will use again the existing property RDFS subclass of. There is no need to define a new property for the same purpose. So let's see how we use it. We have this novel being type class, and then we say that this novel is subclass of, RDFS subclass of book. And then we define book being a class, and we say that book is RDFS subclass of work. And finally, work is defined as being a class. So this is how we define hierarchies in OWL as well. Pretty simple. By defining those hierarchies, we are able to make inferences. So via these inferences, we can say in the end that novel is also subclass of work by following the hierarchy we just defined using the RDFS subclass of property. Also, we can have disjunct classes, because in OWL actually everything might be potentially identical if we don't explicitly state the opposite. So that's why we have the OWL disjoint with, to explicitly state that things are disjoint when they have to be disjoint. Let's see the example. So book is of a type class, writer is again of a type class, novel is a type class and subclass of book, poet is a type class and subclass of writer, and then we did not explicitly state that book is OWL disjoint with writer, meaning that if an instance is of a type book, cannot be at the same type of a type writer. Do you remember our initial example with the class woman and man? It's exactly the same thing here. And again, we can have inferences, and if we follow these hierarchies that we defined and the constraint of coming with a disjoint, we can say that novel and poet are also disjoint classes. Apart from disjunctions, we also have equivalences here. So if we want to denote that two classes are equivalent, we use the OWL equivalent class. So here we say that writer is of a type class, author is of a type class, poet is of a type class and subclass of writer, and we denote that writer is equivalent to author. So if we follow again the inferences here that come after the hierarchies and the OWL equivalent class, we can denote that poet is also an author. And the same concepts of individuals and disjunctness apply also to disjunctness and equivalence. They apply also to individuals apart from classes. So let's see how we define that two individuals are identical. So here we use the property OWL same as link, same as to denote that. So if we have an instance 1984 of a type novel, you see here that there is a property author and property publication here, but apart from those that we have already seen, we see also that there is this OWL same as to another instance. In this way, we denote that the instance 1984 and the instance Rx 012345 are equivalent instances. And then again, we know that novel is a class and subclass of book, and book is again a class. So, of course, here by inference, we can also say that this Rx 012345 is also a book, since the equivalent instance 1984 is of a type book. And also we have the disjunctness, which we denote using the property OWL different from. And this is how we use it. So we have an instance here, Rx 012345, which is of type novel, and we denote that this is different from the Rx ARX 012346. So, in the next part of the lecture, we are going to go deeper and see even more characteristics of the web ontology language OWL.